Did you guys hear the lady say something? Okay, cool. I didn't hear it. That's really weird. I hope everything's being recorded. Ooh, now I'm all nervous. Hopefully, this is gonna record. Then, we'll find out. If not, okay. Oh, good, Brian, you're here. So in case this doesn't get recorded, everyone is here on the cohort. So at least that's this. Anyway, cool. We'll see what things go. It keeps popping up. It's making me nervous now. All right, so I'm going to share my screen, and I just have a couple things to share about the repo. So I think too, I kind of had this idea actually this morning, is I think we'll go over maybe some Git stuff in the near future, possibly even Friday feels. But that way you guys can kind of get a practice of how to do like forks and all that kind of interesting stuff, especially pull requests. I think we might kind of do a walkthrough. Because I was looking at my stuff, I'm like, oh, I'm trying to organize things, and if you guys want to help me organize this repo, that would be cool too. Or if you guys find, like, oh, Victor messed up on the spelling, or he wrote up this code and doesn't work anymore, you can do this stuff. But I wanted to point out that I did start playing around with adding a little README to help it a little more organized of like what module for each of these in the repos. So if you have it forked already, or if you cloned it, you might need to do the refresh to basically pull basically this recent information. But this way you can quickly find the different notebooks that are associated with these sections. So, because I noticed that this is starting to get a little bit a little hard to handle. And note that I put version 2.0 since if we do change versions or whatever, they'll kind of update it in that way so you know if there's ever a difference. Okay, cool. So we're actually going to go a little bit back into section 20. So section 20, we were starting to talk about hypothesis testing in general. We talked about experimental design really very briefly, p-value, null hypothesis, alternative hypothesis, right? When we stopped at effect sizes. So we talked about effect sizes and say that basically it's a metric for us to quantify, how much of a difference there is. One thing to note with effect size was especially Cohen's d. First of all, well, effect size isn't just Cohen's d. Cohen's d is just one way to represent this. There might be other metrics that other statisticians or other data scientists might be using. And just kind of know that in general, it's just showing if there's a difference between two different samples. Now note that for Cohen's d is that if you have a difference, but it's a much larger spread, you just won't have a larger Cohen's d metric, right? So, or statistic. So just be aware that you might get a very small Cohen's d. I think Jenny talked about this in the one-on-one, so that's why I'm bringing it up. And he's like, oh, like it looks like there should be a bigger difference, but it seems like the Cohen's d is very small. That might be because of the variance based on the equation, okay? So just kind of know that there's those parts. So it's always useful to graph things out to see what does it actually look like. Then you can at least visually kind of get ideas like, well, okay, I think I know why Cohen's d should be big or small. Okay, cool. So we're going to talk about t-tests and type 1, type 2 errors. So I'm actually going to talk about types of errors first. And so we kind of talked about hypothesis testing in general. So type 1, type 2 errors will actually be a common theme, not just for statistical tests, but also when we get into machine learning and other classification tools. Because basically it's saying, what happens when you make mistakes, like what kind of mistakes are we making? So one thing to kind of know is that like, when we're talking about statistics, we're talking about a field of imperfect knowledge. Like and the idea that we're doing statistics, it means that we don't know the full population usually. Like that's the whole point of us doing statistics, to summarize this part. And so we don't actually know what quote unquote the truth is, right? So one thing we have to do is like know what kind of mistakes we might make. Now, this is going to be true for hypothesis testing, saying like how you collect this data, but this can also be true for when we do machine learning and classification of saying, make sure we don't make mistakes. But even if we do make mistakes, we need to be aware of what mistakes are we going to make, okay? So when we do get it right, we call those basically true positives or true negatives. So you can imagine if you're classifying someone as sick or not sick. So imagine if you are using hypothesis testing to say, is there a difference between someone who is sick and someone who is healthy? And say, is there a difference between someone's like, I'm trying to make something really simple, like weight, right? So you can like measure someone's weight, for example, and say, oh, are they healthy or sick for this certain disease? Okay. The ones that we say, oh, they are healthy, you could say that's true positives. Say they're sick, they're true negatives. You could have it reversed. Note that it doesn't really matter which one you think, say positive or negative, right? But the point is like whatever's positive, you got correct. Whatever you got was negative is also correct. So there's this nice little graphic that I found on Wikipedia. I actually think the curriculum might have an updated version that they made themselves, but I like this version since it's on Wikipedia. So note that sometimes you'll hear this. You don't need to necessarily memorize this, but you'll sometimes hear this, especially in the medical area, maybe even in psychology, sensitivity versus specificity. Basically, sensitivity is saying, you know, how likely are you, or how many true positives are you getting? What's your true positive rate? So you can think of that as being like, how many of the actual positives, like of the actual positive you have, did you get, or you marked as positive? So you said, okay, all these people in this green like rectangle right here, those are truly, these are the people, let's say, who are sick, right? And that's what we'll call as positive. So these are the people who are actually sick. And your test, for whatever reason, marks only a small portion or a certain portion of these total people who are actually sick. Maybe their symptoms aren't as strong, or maybe their, you know, factors just weren't in that range that would mark them as sick. So you only mark them as this. So sensitivity represents saying how many of the total people who are sick did you actually mark as sick. Okay, so you can imagine this is about like, if I counted this out, this is 4, 7, 8, 9, 10, 12, and we got 5 out of 12. Okay, so 5 out of 12 people, that would be your sensitivity, right? So your sensitivity can at most be what number?
At most one, right? If they're the same.
I'm sorry, Jay, I can't hear you.
Oh no, still can't hear me.
Can you guys hear her? Oh no, it's me.
Yeah, I think it's very clear.
Well, this stinks. Can anyone else speak, maybe? I'm gonna see, maybe. Okay. 1. Oh, good. Lauren's doing the 1. Awesome. And I see Jenny put out probably in the chat too. At most 1. Good. All right. So maybe it's just on my end. Hopefully things are recording. Oh well, I guess you guys are all here, so whatever. Yeah, so at most 1, right? So note that basically it ranges from 0 to 1. 0 meaning that you got none of the true positives, right? You had no 0 true positives. And then 1 meaning your true positives equal the actual positives, right? The number of people who are actually sick. Okay. Similar to this is specificity. Specificity is true negatives, right? So it's saying of all the people who are not sick, negative, right? In this gray box over here, this red is only including a portion of them. So also note that those will be basically, I'm sorry, all the ones in this outside of this circle part right here. So if you imagine just this kind of like, I don't know, a little blocky shape, like a little chunk taken out of it, that would be the true negatives, right? So only a portion of these would be true, marked as true negative. And so basically know that like these are independent from each other, right? That sensitivity and specificity don't have to actually match in any way, right? You could do things. What's one way you could guarantee to get a sensitivity of 1? Like you don't know anything about the test, but what's an easy way to make this work? I realize I'm not going to be able to hear you guys probably, but I'll maybe have you guys kind of think about it a little bit. Good. It's on the chat. Just say everyone has a disease, right? So if everyone has a disease, regardless of what happens, you will always get 100% true positives, but your specificity, right, will be 0, right? And you can see the opposite. If you said no one has the disease, well, then you will have your specificity, your true positive rate, 0. I'm sorry, 1, but your true positive rate is going to be 0, okay? So just kind of know that basically there's that little bit of trade-off. So we want to balance in there. We want both to be 1, but note that you can kind of, in a sense, cheat the system. So this is why we break these down into different parts. So that's how we get things right. When we want to get things wrong, or if we get things wrong, okay, we call these false positives and false negatives. So I think most people have heard probably this term, even if you weren't ever in science, probably a false positive, false negative too, but like I think this is more concerning when we do a false positive. So yeah, like I said, you've probably heard this from like from a TV show or, you know, just from culture, just osmosis, right? Note that we denote this with this symbol here, which is alpha. So alpha basically is going to be our false positive rates. And we're actually going to use that to determine how much are we allowing a false positive. It says how much we can basically, how much of a percent can we actually get wrong? And usually we'll talk about it as being at 0.05, but it depends on the field and experiment, right? So certain fields or certain experiments require a higher false positive or a lower false positive rate. So if we had an alpha of 0.01, we're saying, oh, we won't accept this. We'll accept only a smaller false positive rate. So, okay. And false positive just meaning that you get the ones that you basically, trying to phrase this in a good way, your false positive rate basically is saying the number of times that you actually say, oh, this is true, when in fact it wasn't. Okay. All right. So, and then our false negatives, right? Our false negatives are going to be very similar. Note that we also tend to call it beta. Oh, I also should mention type 1. You'll hear type 1, false positive rates, alpha. Those are all the same thing. And similarly, false negatives, type 2 errors, and beta, that's what the symbol is. These are our second, type of errors. This is why I kind of remember it. It's the second type of errors. It's the second Greek letter, beta. I don't know if that kind of helps, but I try to tie them together in some way. I don't have a good one for alpha, and then I guess alpha is the beginning, right? So you could try to remember it like that way. And usually we're okay with this about being 0.2. Note that later in a second, we'll talk about statistical power. Statistical power will be the inverse of, not, I guess inverse, I guess the complement of beta. So statistical power will be like usually 0.8, which means beta will be about 0.2. Okay. Cool. Note that we tend to accept more false negatives than false positives, but this might not always be the case. So sometimes you might care about which type of error you actually want, right? Depending on what kind of test. So if you imagine, like, for example, different medical tests and stuff like that, you might care more about the false negatives than the other one, right? So classic example is like the pregnancy example. This is kind of like a little funny picture to help you remember, right? A type 1 error basically is saying, oh, you're a false positive, saying a man basically you're pregnant. It's like, well, that seems very, very unlikely, right? So false positive, right? Or this is a false positive type 1 error, right? And then type 2 error says you're not pregnant when you actually are pregnant, right? So note that we tend to be more okay with making false negatives, usually because then the next part going through. False positives, might lead to more, honestly, more stress, more, what's it called? More tests, more kind of like assumptions that, you are like, sick and you have to do a next part test. So they try not, like usually in the medical field, they try to avoid this, but there's some cases where maybe you actually do want to care about type 1 errors over type 2. So imagine, so I'll give you a little quick scenario, and this is more like to kind of think it through about like your disease. Like imagine this disease. So disease is very, very deadly, right? What matters more in this case? Would type 1 error matter more or type 2 error matter more? And this is kind of opinion, but what's your kind of gut say? I'll give you guys like 5 seconds to kind of think it through, and then we'll all share. All right, cool. So Lauren says false negative. So is that type 2? Type 2? Yeah. All right, Jenny, and I see type 2. Yeah. So yeah, probably in this case, what error matters more is that you don't want to miss a very deadly disease, right? You want to make sure, like you might make some more false positive rates or make some more false positives, but that means you'll catch everyone who does have the disease, right? Or you're more likely to catch someone who has the disease, that we can catch them quickly. Now here's a little quick thing. It's like maybe same deadliness, or maybe still serious, or maybe just not serious, but the disease is very rare. What error matters more? So that means very few people have this disease. I'll give you guys 5 seconds, and then you can just do either 1 or 2 with your fingers. So type 1 for false positive, type 2 for false negative. So I'll give you guys like 5. Okay. So I see 2. Okay, good. So I see them. I see Jenny do 1. I see people do 2. All right. So disease is very rare. So we'll kind of work this out a little bit verbally, right? And I unfortunately can't hear you guys, so I like you guys to explain. But just kind of tell yourself like what the reasons are, and then we'll kind of talk this through. So disease is very rare, which means that very, very few people actually have this disease, which means that you will likely have more just false positive rates, right? So if your false positive rate remains at 5%, but most of the population doesn't have this disease, well, you're going to get a lot of people, like the majority of people you test will actually get, will test positive for the disease, where really only like one of those people who tested positive actually have disease. So you might actually say the false positive rate actually, or the type 1 errors actually matter more. So you'd want to make that as small as possible. That way you make sure that you're not testing like 5,000 people just to make sure, they don't have this disease. This is actually an interesting kind of concept. For example, I think I'm gonna mess up this disease, or it's the one with it's I think it's cervical cancer. I can't remember the test for cervical cancer and stuff like this, because men can get it too. But they talk about who should test, and they were saying, oh, everyone should get tested. So the problem is that if everyone gets tested and it's not super common, the problem is that you might start getting more positives, and some of the tests can be kind of invasive and stuff like this, and cause a lot of harm in the sense of like not just physical harm, but like psychological harm, being like, oh no, do I have cancer? Do I not? So they actually were saying maybe you should step back of saying who you suggest to get these tests. And that's honestly kind of controversial in the sense of being like, what is that cutoff? Because you could potentially save someone's life, if you catch a disease very early. But if you have to test every single person, right, for this disease that's maybe not super common, then you might cause extra harm or actually have it difficult to find the disease or find someone who has this disease. And there's a whole bunch of things that you have to deal with. So anyway, I would say type 1 error actually matters more. But you could maybe argue for type 2 as well. Okay. I'll kind of skip over this part because we're kind of going a little wrong. But just think of other factors that would affect the errors or make the errors matter more, whether type 1 or type 2 kind of thing. And right now I've talked about disease right there, but you can also extend this further. So the justice system. So I want you guys to think a little about the justice system, like how we kind of structure it, at least in the United States, right? Other countries might have it structured a little bit different. When you think of a type 1 error in this case, I'm just more talk this through rather than discussion. When we say type 1 error, there's a type 2 error. When the justice system, we say someone's either, basically we put them in jail, right? Or, fine them or whatever it is, right? They're guilty or they're not guilty, right? So a type 1 error would be like, oh, you're false positive, which means that you're not actually guilty of the crime, but we declare that you are guilty. Versus a type 2 error, which would be, okay, you are in fact guilty, you did commit the crime, but we say, oh, not guilty. And, you get away with it scot-free or whatever, right? So thinking of those two different errors, type 2 basically meaning that you caused the crime, you did do the crime, but you got away with it. Type 1 error, you didn't do the crime, but you got blamed for it, okay? For the US justice system, which errors do we care more about? Or at least how, like what, I should say maybe not necessarily society, like, I don't know, maybe you can kind of say like either society or like how it's built around, or, what does it seem to be built in? And I see some like, one's kind of sneaking in a little bit. I saw Brian's earlier, right? So yeah, false positives, right? For the most part, we kind of don't want to put innocent people in jail. And that's where you can even hear the phrase, right? Innocent until proven guilty, right? We usually were more okay with the sense like, well, we might have some people get away with, crimes, but we're more like, we in practice, or not practice, but in theory, we don't want to put these, innocent people in jail. Do false positive rates happen, or false positives happen? Unfortunately, yes, right? And so there's a whole bunch of, debate about like, how do you structure this system? But you can see now, viewing what the test is the justice system, right? Saying, person going into guilty or not guilty and related to type 1, type 2 errors. Okay, cool. If there are any questions, I guess you can maybe put it on the thing to the little chat at any point. If you guys have questions, just put it on the chat. That'd probably be easiest. But sound pretty good right now for 1 type 2 errors. Awesome, cool. So now we'll go into our t-distributions. Okay, so for t-distributions, this will lead us into our t-test itself. And this will be kind of like I said, a little bit like, I think I mentioned this last time, is a t-test and a t-distribution is actually very similarly formed with a normal distribution. It basically is not estimated, but it's like a modified normal distribution, or Gaussian, right? So this is a little quick history. I think the curriculum might talk about this, but I think it's a really cool fact. Okay, the student's t-test was by William Gossett. I think Gasset, I don't know how to pronounce his name, but in 1908, right? Turns out he actually worked for Guinness Breweries, the same Guinness, who makes the beer today. He actually had to publish under a pseudonym, basically speak of student, because Guinness wouldn't allow him, the statistician, to publish under his own name because he was working for Guinness. So basically that's why it's called the student's t-test, or t-test, or t-distribution, right? So kind of sad. It should be kind of like the Gossett distribution, but oh well, right? It's kind of a fun fact. Anyway, he also was doing this because he was trying to make better beer. So, beer leads to good things. All right. So the real reason why I talked distribution, it basically is like we don't know the full population distribution. So that's kind of like what this comes from, is the fact that it's like the z-score assumes that we can get a normal distribution from this part, but we kind of don't know what the population actually looks like and how likely it is for us to get a normal distribution from any given sample. So the t-distribution allows us to say, well, we know from the central limit theorem essentially that we would eventually get a normal distribution if we took many, many samples and those samples means. So essentially what we're doing, and I'm really paraphrasing here, like doing little hand waving stuff, is that essentially what we're doing with the t-distribution is like, well, we don't really know, so we might actually get more extreme parts in the end. So that's why we get these things like what we call like these heavy tails. And so you can see here, I think this is from the curriculum as well, or something similar on this on the curriculum, is that we can see in the blue here is the actual normal curve. And as we get more essentially samples, which we will call kind of related degrees of freedom, which we'll talk about maybe in a little bit. But as we get more and more data, as we get more and more individuals in the sample, right? Essentially what happens is that we're more likely to approach a normal distribution. So you can see here in this red here, basically getting closer and closer to this normal distribution. And in the green here, which is kind of tough to see a little bit, but those are the past ones. So you can see a degree of freedom 1 versus degree of freedom 2, degrees of freedom 3, and you can see it gets closer and closer to the normal distribution. But the part that I want to kind of point out is that note that the tails here, we'll call this like heavy tails, that the values on these tails are a little bit higher than it would be on the normal distribution. And that's because we're accounting for the fact that we might be pulling more extreme values from a distribution that is not actually normal. So this is kind of like what we're keeping in mind. And that's why as we get more and more individuals, you're less likely to pull more extreme values and more likely to pull values that are closer to the actual mean. Okay. So, and you can see here it goes all the way up from 5, 10 degrees of freedom and 30 degrees of freedom. And note that it's not explicitly stated here. I don't even recall if it's stated explicitly in the curriculum, but usually at least 30 samples, we consider that like that's good enough essentially to make a statistical test. You can technically make statistical tests like with lower amount of individuals, but usually we say 30 is really when we can start saying something useful. And the real reason why is because it approximately, it's approximately normal distribution here. And I see from Lauren as a t-test equal to distribution. Yeah, so t-test will actually use a t-distribution. They're technically two separate things, but the t-test is going to be using the t-distribution in the same way that a z statistic is using the z, well, there's no z distribution, it's the normal curve. So essentially that's the equivalent there. So if you're familiar with a z-test, for example, essentially all you guys say, okay, basically you're calculating a new statistic called the t-statistic, which we'll talk about in a second. And then from that t-statistic, we'll actually use the t-distribution to find the p-value. Okay. Cool. All right. Anyone, any questions, I guess, other than that on the chat about t-distribution, at least the way it forms? No? Okay. Cool. All right, so one quick thing about confidence intervals, because we talked about a little bit confidence intervals with t-distributions. I think it's going to be kind of useful. So I'm just going to show you really quickly is that if we wanted, for example, a confidence interval of 0.95, we can use a statistical t-distribution, right? And use that interval to calculate our confidence interval. So note that this right here basically are different values. In this case, you can see I'm using SciPy. I tend to use SciPy more than stats model, so just kind of know there's a little difference maybe sometimes from the curriculum, though I think the curriculum kind of goes back and forth a little bit. But basically I'm using the stats.t.interval, so this is built into SciPy itself. And you can see I have alpha, which we already know is essentially our false positive rate. So essentially what we're saying is this confidence interval is saying, okay, we want to fit 95%, 95% of our confidence intervals should include the true population mean. Okay, that's essentially what we're building our confidence interval around. And then our degrees of freedom, 99, which should be actually, usually we do for a t-distribution or t-test, it will be the number of samples minus 1. So this would be 100 samples. Okay, so 99. Location basically just representing the mean, right? So 65, I'm just making up data here. Scale is 18. So 18 is a pretty decent size standard deviation. So we'll kind of see how that turns out with actually finding our confidence interval. So I run this now. I'll actually get our confidence interval, right? Of 95. interval start, interval end. So this will actually have a beginning and our end. And we can see here our confidence interval, which remember we said the sample mean is 65. To say that means that 95% of our, we have a 95% confidence interval from 29 to about 100. And basically that's saying if we were to repeat this, we would expect our samples would include the population mean 95% of the time within this interval. So, so basically we was like the population mean is somewhere in there. Okay. Okay, I see 1 minus confidence interval. I think actually in this case, I could be wrong. I think you're right, Lauren, that it should technically be 1 minus, but let's see here. Yeah, you're right. I think it should be 1 minus. Maybe I made a mistake here. Yeah, so this should actually be good catch. There we go. Much better. Okay, so this is allowing, again, a smaller false positive rate versus 95% false positive rate, which is pretty high, which actually makes sense why it's such a huge value, right? So you can see here is that between 63 and 66 here. And note that as we increase the, if we were to decrease the degrees of freedom, so if we had less in our sample, would we expect this confidence interval to get bigger or smaller? So they had like only like 11 people. Yeah, I see people say big. I see Jenny say bigger. Yeah, so if we have less people, it means that basically we're less confident, right? So we should have, we went from 63.8 to 66. So if we have like 10 people, you can see here, it gets a little bit bigger. But this is nice because it might depend also on the scale as well. That doesn't seem quite as right, but let's see. If I make this extreme. Okay, it is technically getting bigger. But I would expect it to get bigger than that. Okay. I don't know. This might actually be part of the statistical t-distribution itself is why I'm getting this huge difference. Now I'm wondering, why did I have this before? I almost wonder if I had something where this is SciPy does something strange here. No. Okay. I'll have to come back just to think about it a little bit. Or, you know, we'll go look at it right now, right? So SciPy, what was it? T dot interval. So this is how you look up and see what's going on. So you can see here, oh, look, gamma function. Okay. Students continuous, and we can see here, sometimes the, and this is T dot stat, but I want T dot interval. So let's see if I can go back one before I look for it. No. Okay, this might just be in it. Okay, so let's see if we can find it, calculate an interval for us. No. Okay. I think Lauren's right, but I'm just kind of scratching my head and like, why did I put something different? But maybe I'm wrong in this case. Oh no, okay. I think I was right in this case. Unfortunately, I think Lauren, it would make sense that it should be alpha, like 0.5, but I think for the t interval itself, it's actually supposed to take in the confidence interval itself to find that interval, even though it says at alpha, which unfortunately makes it super confusing in that sense. But, you know, so is life, right? So yeah, so it should actually be, where am I at? Okay. So this should be, good thing I looked it up because so, okay, that would be, and this makes more sense is that this interval was bigger. So if I had like 100, we should see it get a little bit smaller. You see that? Okay. And that's because partly because of scale. So if I make this scale relatively small, we'll see our interval get a lot smaller too. Okay. So this is where it's always important to kind of like look for documentation just to double check. You can see here, yeah, unfortunately, alpha does not really make sense because it really should be a confidence interval. And this is where, you know, Stack Overflow and other people, you know, checking it out and everything like that. But anyway, okay, moving on. Cool. So quick, kind of just showing us sample data. So making some quick data, norm of a mean of 54, 17 being like the standard deviation of 500 people. We're basically just going to go ahead and just plot out this bin just to kind of check it out. So I just want to show you guys what this would look like if I had 500. And you can see here, this is the plot going on. And you can see this interval here, alpha 95, our samples -1, sample mean, sample standard deviation. And we can see that we say our true population with 95% confidence, right, is between 19 and 89. So you can see here is that essentially we have this long stretch of things. If we increase though to, let's say, how many do I have on here? 100,000? This might take a second. So we'll see if this takes a second. There we go. So you can see it very close to a normal distribution, and we should hopefully get a smaller part. But note that we always like still have this uncertainty and saying like how much are we allowed to really hone in on, because we want a higher confidence essentially. If we want a lower confidence, like, well, let's say we're fine with 85% confidence interval, you know, for whatever reason, this interval would get smaller, but it means that there's a chance for us to like basically our sample interval is not going to be contained. So essentially what this interval is going to do, essentially it's going to take this data and say, if I took this data and just randomly picked it out, what would be basically the interval that would go across this part that would include. And so 85% of these intervals would include the true population mean, which in this case was what, 54, I think. So it should be about right here. So which looks about right for, what was that, 10,000? Yeah, something like that. 100,000? 100,000. Okay, cool. Awesome. Any questions, I guess, on this guy? Sound pretty good? Okay. All right, yeah. Yeah, I'm glad we talked about this one because that one, I should probably put a note there next time, but we'll see. Okay, so this leads us now into our actual t-test. So now we're actually going to use this t-distribution here and move it into performing a t-test. So I'm going to kind of walk through the steps a little bit. To be quite honest, once you understand how a hypothesis test works, you can basically take any test and just replace what we talk about, like a t-test versus an f-test versus even possibly an ANOVA and stuff like that. Essentially, you're just replacing the statistic with the distribution and you get a p-value. So just kind of know that this will kind of flow for pretty much every statistical test you do. So our t-test, so very similar to our z-test itself, we'll get something called a t-statistic, which is basically something related to, it's a summary like of the data that we're looking at. And then that t-statistic will give us a summary, oh, I literally said that, summary of the data, and it's approximate distribution, right? So essentially, the reason why we get this very specific t-statistic is it's based on not just the data that we have, but also the distribution that will come about from the degrees of freedom that we have. So if we have many, many data points and we have the same mean, for example, the same standard deviation, that's going to be very different just because we're going to be more certain by having more data. Okay, we're going to be closer to a normal distribution. And we'll use this t-distribution and t-statistic really to decide if we want to reject the null hypothesis. Okay, so right here, we can use a t-test to compare sample means. We don't know the population standard deviation and large n. So note that basically we're using this to compare kind of like in the same way that if you had two different samples with the z-test, you can say this is what's it called? Well, I guess usually the z-test we're talking about as being like, does this sample belong to the population? So here's like saying, okay, does this sample belong to the sample? So are these groups the same or are they different from each other? Okay, and we always perform it with, you know, a large data set. You'll see this in like textbooks, like in statistics being like large, and large usually means greater than 30. Again, this is relatively arbitrary, but it's backed up by the fact that it's close to a normal distribution here. Okay. Note that we should always pick our alpha before performing the tests. This is, I can't stress this out more enough, is that this will prevent you from, you know, basically p-hacking, is that you want to decide not just like, I think the standard usually is 0.05, but you should really think about like, is 0.05 make a lot of sense for this specific field, this specific area, this certain experiment. So those are factors of like what you're okay with. Okay, but after doing that, you're like, okay, I know my data is large enough. I'm going to compare two sample means, you know, in some way, and I'm going to, you know, use this alpha. Then you go for the next part, which is our assumptions. So this is an important part because if these don't pass through, you have to be careful about, you know, interpreting your data. Independence, randomly sampled, we talked about these things. Population is likely normally distributed. When I say population data, I really should say population sample means, which I mean from central limit theorem, you should be getting this from here. So this is usually kind of like the weakest of like these assumptions. In reality, can you perform the t-test if some of these aren't quite true? Yeah, probably. In reality, usually the t-test will be performed and say, okay, just be aware of ways this might fail, or say, okay, like if it's close, you might want to be a little careful and be like, okay, were all my assumptions clearly met? Like, is this something I need to worry about? It's kind of a running joke a little bit when in statistics. It's like, do you really care about the assumptions? Because a lot of times we'll just run this t-test regardless. But usually it gives us good enough results because, you know, if you think of it this way, if you believe that the universe is not completely, what's it called? Like, it's deterministic in some ways, which, you know, you would say, oh, there has to be some deterministic, you know, tendencies, right? Nothing's independent. So you can kind of see like independence never is completely true. But that's kind of like meta philosophy kind of stuff, but we're not going to worry about that. So just be aware those assumptions are needed. So our steps, so this is the good stuff, right? This is the stuff that we actually care about. So the first thing to do is really say, what are you testing? I cannot stress this enough, which seems really basic. Like you're like, hey, you should know what question you're asking, but you'll be kind of surprised how many times people, you know, will kind of like start doing this test and like, wait a second, what am I even like testing out? So it's really good to like determine exactly, and I would say like literally write down your null hypothesis and your alternative hypothesis. I think this is just good practice, and it will also guide you to make sure you don't, you know, make mistakes, and also you don't make the wrong conclusions. Okay. So next part, basically, after you kind of write down your hypothesis, like, okay, I'm going to say, this is my hypothesis. Is it going to be a one-tail test, a two-tail test? Basically saying, are the population means different? Or not population, the sample means different? Or the sample means, you know, one's bigger than the other? It might depend on what you're really asking, right? Once you have that, you determine your alpha. So usually 0.05, but note that you might, you know, modify that depending on, usually on the other end of making it smaller, depending on like what your field is. So if you are using a field that is very, very, like let's say people are very, very precise, you know, things are very precise measurements, you might actually have a much smaller alpha. Like I mentioned in particle physics, they do many, many experiments, like literally billions of experiments, you know, with collisions and stuff over and over and over and over again. And they're very precise measurements. That alpha has to be relatively small because basically if you have so many, you know, possible interactions, plus the fact that you're measuring it really precisely, you have to make sure anything essentially can be a slight deviation from it might cause a false positive. So you don't want to do that. Okay. So the next part basically is get your t-statistics. Get your t-statistics. So you have your data, right? You have your alpha. You know what you're going to test. So now you actually say, okay, here's my t-statistics. So it's very, I don't know, anticlimactic right now, is that this is our little equation right here. In reality, would you calculate this yourself? Probably not. You can, for the most part, use a package and it's going to calculate the t-statistics for you without you even having to think about it. But just know that basically it's related, very similar to like the z-statistic. So note that basically we have our sample mean here minus the population mean, or when I say population mean is meaning the mean that you're testing against. So if you're testing group 1 and group 2, this would be like group 2's mean right here. Okay, so sometimes you'll see this as like x bar 2 minus x bar 1, same idea. Okay, and then S meaning the sample sample deviation, right? So basically the standard deviation of the sample, that's what that S represents, and we divide it by the square root of n. And the reason why we divide by the square root of n is essentially we're saying is that if we have more in our sample, right, we're more confident that our spread's going to be relatively small. If our spread's still very large for a large n, then our sample standard deviation really should stay that large. But essentially that's what we're doing right here. If we have very few, if we have like 5, right, different samples, and our standard deviation is relatively large, it really should stay relatively large because we could have gotten very extreme values. But as we get more and more and more, we can assume that we're going to get most of the stuff that's kind of representative of the population. Okay, cool. So any questions on how the t-statistic is formed? Hopefully it doesn't seem too complicated in that sense. Essentially, it's just, again, like you can read this as saying how many standard deviations or sample standard deviations are you away from not population, but the other group's mean. So how different are the two means? Essentially is what your t-statistic is saying. Okay, and note your t-statistic. Can this be negative? Negative. I see a head shake now. It can't be negative. So if you have the mean actually smaller, sample mean smaller than the other sample, then it can be negative. Can this number be bigger than 1? Yeah, so it can be bigger than 1 because essentially it's saying how many standard deviations are you away? Well, you can be many standard deviations away from the actual mean, right? If you imagine taking the weight of a mouse and then the weight of a human, and then saying, find the C6 from there, you're going to find it's pretty significantly different. Like if you're a mouse versus a human, your weight's going to be different. So that kind of makes sense that your larger t statistic is saying to what extreme it is. Note for your t statistic, like I kind of said negative and positive. Sometimes in reality that doesn't matter as much because in the sense that if you're doing a two-tailed test, if there's just a difference, you don't care if it's positive or negative. But if you are saying, for example, humans, your first hypothesis, humans are heavier than mice, right? Essentially that you can think like x bar 1 or say mu1 is greater than mu2, then you say, okay, that would be like maybe a positive, right? You would say, okay, you would expect it to be a positive value. But if your hypothesis test was saying mice were heavier than humans and you get a negative C statistic, you're going in the opposite direction. And basically you would fail to reject your hypothesis because duh, right? Like mice are actually much smaller than humans. I'm going to say yes. So, okay. I'm trying to see if there's any counterexample, but I couldn't think of any. All right, so note for like finding your critical t-value. So this is where I'm going to make a little kind of note here that's not, in my opinion, really clear sometimes. So you have a few things. You have your t statistic, which is also sometimes called your t-score, which is super fun because no one, like people just use different words. But your t statistic, right, your kind of your t-value, that's what you're kind of talking about here. That's what this is. Your critical t-value is basically saying taking your alpha value, which is also called your critical value, taking your alpha value and translating it into the t distribution. So before it was really easy because your alpha value for your normal distribution correlated perfectly with your critical value. But since we're using a different distribution, we would have to convert our critical value, or alpha, into this critical t-value, which is also sometimes shown as t star. Let's see if I can write this really quickly, just to kind of show you guys. Sometimes you will see it look like, oh, this works. I don't know if my LaTeX is good enough. So you'll sometimes see your t critical value like this t star here. That's what they're talking about. Essentially, they're converting your alpha value into the distribution, this t distribution here, to get your t star or t critical value or critical t value. Does that make sense to everyone? Okay, cool. I wanted to make that distinction because it can be super confusing. Okay. So once you have your critical t value, you basically plug that, you basically say, okay, this is what I need my t value. So you say, oh, my critical t value is, let's say, like, I don't know, let's say 2, right? Whatever alpha you put in it, you get 2. So that means basically your t value has to be bigger than t, or than 2, in order to say it's significant. Okay, essentially that's one way to do this. Another way to do this is essentially you take your critical t value, okay, and bear with me here, but you basically have your critical t value and you convert it into a p value. So you could do one of the two ways, but basically just know essentially what you're doing is you're comparing it with a distribution. So in the long run. Okay, so once you have your critical t value, for example, and this is usually done by a package, usually you're not doing it yourself, you can see here this is your critical t value in green on this bar right here, and then we can see this red right here basically being your actual t statistic, your t value, right? And say, oh, it's significant, and you can say, okay, it's greater than this, that means we can reject the null hypothesis that there is no difference, or they're less than or equal to, right? So this is basically the main parts. Our 1 sample and 2 sample are relatively I think they're not too difficult to understand. Essentially, they're just different scenarios. I think sometimes it can get confusing in the sense that we call them 1 sample, 2 sample, but that's just me. So a 1 sample, you can say, is your sample different from the population. So you can think do Snicker bars actually weigh more than 120 grams than it says on the package? So on the package, it says 120 grams is how much this Snicker bar weighs for whatever reason, right? And you can take a population, say randomly, random sample a bunch of Snicker bars, for that they're supposed to come from that bag or, from that same production, and see if they actually weigh under 20 grams, right? So you probably in this case, you'd want to do a one tail, one sample. One tail meaning that you actually care about it being less. If you cared about it being less than or greater than, just saying maybe they just messed up on the packaging, you would do a two tail, meaning that you care about both sides. So you imagine like not just this part right here, but you'd also care about this one here. Okay. And that's important to note that you should know before you even do the test if it's going to be a one tail versus a two tail. Okay. That makes sense to everyone on like that scenario? Cool. You can tell I was kind of hungry when I wrote this. So, all right, two sample. Let's see if it's less hungry now. All right, so two sample. Do the control group and treatment group of a drug trial differ? So did the drug have any effect? So this might also be between like two different drugs. You know, you're just basically testing between two different samples and saying, do these are different from each other? No, it's a little subtly different than the one sample where usually we're talking about a full population. Say, is this like a special subgroup of people? So for example, one sample could also be like, does this subgroup, you know, candy collected on Halloween, you know, are they significantly different from the normal, you know, or to normal, the typical package versus here with two sample, we're talking about, you know, you have a full population, you're comparing two different groups. Like this could, for example, even be instead of control group and treatment group, it could be like, you know, for example, men and women, you know, and say, okay, we give the drug to men and women, you know, is there a difference between these two? Or we give a drug between, you know, ages, you know, 5 to 13 and then 13 to like 18. Is there a significant difference between, you know, the effect of this drug or something like that? Okay. Cool. But honestly, I wouldn't stress too much about trying to figure out if it's one sample, two sample, because it's like basically like the same thing. Like you basically have a sample, or you have your sample and then you compare it either to another sample or you compare it to the population. Cool. Any questions on this? One sample, two sample, sound pretty good. If you want to just write in the chat. I think I see Lauren typing. I'm not sure. Okay, good. So I'm so sorry about it not like working this. I gotta figure that out. So while she's typing, okay, good. Do you mean to compare another sample of a population that depends on one or two samples? Do you mean to compare to another sample of population that depends on one or two samples? I think when you're talking about two sample here, is that what you mean, or these guys? This is tough when it's only through chat, right? I would say it's more, sorry, I would read this. You just said it's more important to compare another sample or to the population. Yeah, I don't know if it necessarily be more important. I would say you tend to do things along this end of like comparing two different samples. Is that what you're asking? No. I feel like maybe maybe try unmuting yourself. Maybe it does work.
Can you hear me?
I can't hear you.
Okay, well, maybe anybody else can like kind of. So you said it was like more important to compare to like to understand if you're comparing to another sample or to the population. That's a completely different topic than the one sample, two sample thing, right? Like that doesn't have anything to do with the one sample, two sample. It's just like instead of like focusing on one sample, two sample, focus on are you comparing to another sample or to the population?
Yeah, and that will help you determine whether you're doing a one sample or two sample. If you have a sample and you're comparing it to the population, you're doing a one sample test.
One sample.
And if you have two samples, both from a population, then you're doing a two sample test.
Gotcha. Okay, thank you.
Sounds like Lauren got it figured out. Or you guys talked about it. I caught the tail end. I can actually hear you guys now. Okay, I'll just read this out. We were saying that when you have one sample compared to population, that's one sample, and then you have two samples for population, that's two samples. Good. Perfect. And that answered your question, Lauren? Oh, I can't hear you. You guys hear me now? Okay, cool. I can actually hear you guys now here. I don't know what's going on. stinking Zoom right now. Okay, but at least it sounds like you guys got it figured out, or worked it on everything. Awesome, cool. All right. I'm scared to ask are there any other questions now, but all right. How are we all feeling? Thumbs up, sideways, thumbs down. Okay, cool. And I believe technically, correct me if I'm wrong, I think this section technically talks about like multiple comparisons, like ANOVA. Yes, I see it here now. And Welsh's t-tests. So we're a little out of time, but we'll talk about Welsh's tests, t-tests, and multiple comparisons next time. Which will lead to section 22, because honestly, section 22, there won't be much for me to talk about for A/B testing because we'll talk about statistical power. Well, I just realized I didn't even get to statistical power. Okay, well, that's all right. But next time we'll talk about statistical power, and then we'll talk about Welsh's t-tests and say, what the difference between that. It's relatively the same. For the record, you'll probably use Welsh's t-tests much more than students' t-tests, because Welsh's t-tests will essentially default to students' t-tests when the variances are equal, but it's slightly more accurate when we have those parts. So just kind of know that part if you're trying to get used to like what t-tests to use. But yeah, we'll talk about statistical power, we'll talk about Welsh's t-tests, and we'll talk about multiple comparisons, which will lead us into ANOVA. And then we'll touch on A/B testing, which I still have to try to figure out why people stress out about A/B testing, because it's not as bad as it seems. But I see it everywhere. I always like articles like, how to do A/B testing correctly. And I'm like, I don't know. Maybe I'm seeing something wrong. You guys can tell me. But anyway, sound good? Cool. All right. Oh, I guess I can stop recording then. Sound good? Yeah.